Okay, folks, I'm back earlier than I thought, but we're back here to talk about some of these routing and switching topics. This, by the way, wallpaper of the day, I didn't mention this earlier. This is from the launch, I think it was yesterday, where they're further testing Blue Origin and the little capsule there. Did a successful test of that, which is interesting. Yeah, round two, man. Let's go. Round two. Let's do this. So, yeah, the topics I want to cover today: fast switching, process switching, CEF switching. It's important to know how to recognize when these are on or off. And one way to do that is, of course, via the commands. And let me pull up the drill sheet so we can go over these. I doubt you ever have, I don't know, as far as the lab goes, this is probably more appropriate topic for the written. I don't foresee having to configure fast switching in the lab, but wouldn't put it past them. It's good to know the difference, though. And as a matter of fact, I created here in the drill sheet. This has been a big help to me this last few days. And what I've done is some of the topics that I've recently added or need to work on a little bit, I've marked them in red. The drill, this area where you fill it out is just, it's off the rails right now. I've been just filling out the answers. Later I will go back, copy, paste, redo the whole drill page that you fill out. But in here, I believe, yeah, I know I put it in here. It's big, guys. Yeah, here we go. So this is going to impact, of course, how you will use, how packets are switched, right? Load balanced in particular, how packets are switched and how they're load balanced. So for example, you have process switching, which is the slowest. And if you have multiple paths, let's say you have EIGRP and you have equal cost multipathing working, that's fine. Process switching supports that. But what it will do is if you do a show IP CEF, or no, show IP route, and then you look at, generally you have a star next to where the next either flow will go or the next packet will go. And you need to know what the difference is. And the difference is if you're using process switching, it is going to load balance on a packet by packet basis. Now, that may be preferred, even if you're using CEF, but by default, that's what process switching is going to use. The problem is you have a lot higher chances of asymmetric flows, right? And you'll have pure load balancing in terms of the number of packets going through. Say you have two interfaces, for example. It's going to be it should be a pretty even split. But you're going to have, a high probability of asymmetric routing and issues that come with that, right? And process switching is slower. You have to take up the CPU's time to do this, the central CPU or CPUs. And the way to turn that on, you could do it at an interface level, no IP route cache. And that puts you in process switching mode. Fast switching will use a route cache, right? It's not like CEF, which is hardware-based switching, not taking up any of the processor memory additional. But fast switching, it's a little faster than process switching. It does allow you to do a per destination or per flow load balancing, which is generally preferred. And the way you configure that is you can use, if you've turned off process switching, or if you turn on process switching, you need to turn that off. And you need to say IP route cache. If CEF switching is turned on, then you need to turn that off with the command no IP route cache CEF. Okay? So you've got IP route cache CEF. And there is no IP route process switching. It's either you've got fast switching on or you turn it off to go to process switching. You want to do CEF, you do IP route cache CEF. And that, of course, is a preferred method, and that is a per destination or per flow load balancing. So the key to focus on this here, I think, is the commands, and it will show you when you do, I believe you do a show IP route, it will actually show you which of these methods is in use. So that's important to know. Next topic. Rapid spanning tree protocol port types and states. This is important. I went over this in the drill sheet here. I made a table. I had a table already for 802.1D, which is IEEE STP, spanning tree protocol, right? Then we have 802.1W, which is rapid spanning tree. And notice the port states. So I've got several pieces of information in here. The port states that you have in 802.1D, of course, are disabled, blocking, listening, learning, forwarding. And this should be, sorry, I thought I had fixed this. This should be port types. Now in 802.1W, essentially you don't have a specific disabled state. It's either you have discarding, learning, and forwarding, and this is the equivalent. So disabled and blocking, the equivalent is forwarding. And actually, it should be like this. There is no listening state in 802.1W. There essentially is just discarding, learning, and forwarding, right? So you have learning, and you have forwarding in both. Those are shared port states, but these others are different. Port types. Root, you have, of course, your root and your designated and your blocking in 802.1D, but essentially the equivalent 802.1W is instead of blocking, you have two types of discarding ports, alternate and backup. And the difference in those, I think that's important to know. The difference in those is that the backup is, let's say you want a shared segment, switch A and switch B. And switch B has two ports that are connected on the same shared segment. Well, both of them can't be designated ports, right? So let's say one of them is a designated port, but the other is also a designated port. And it is sending BPDUs, or could be sending BPDUs out to the segment. But switch C knows, hey, I've got two ports that are candidates for designated. One of them needs to be a backup port because you've got another port over on switch A that is also a candidate designated port, but it has been selected as the alternate. So if you're on the same switch, you're likely going to have designated and backup ports. An alternate port will come from a different switch, very likely. So that is the difference there. And then timers. Now this is where it gets important to know, we're all pretty familiar with timers in 802.1D, and you really have to know these for the exam. Your hello timer interval, forward delay, max age, aging time, and then the timers, how they respond to topology change, topology changes. So hello timers is 2 every 2 seconds. 15 is a forward delay. So when you go into listening, you start a forward delay timer. And learning also uses the forward delay, right? So you could have up to like 32 seconds before you transition to the forwarding state in 802.1D. The max age, that's how long you will wait for a new BPDU. And then aging time is 300. So that's when when you're listening, you start to learn the MAC addresses and which interfaces they're on. The aging time for that is 300 seconds. Then you have the topology change. When you receive a topology change BPDU from the root, In 802.1d, the root sends a topology change. And it does it when it receives a topology change notification from a downstream bridge, right? When it does that, it sends a BPDU with TC flagged, and it uses a forward delay, the same as a forward delay timer, 15 seconds, to send those TCs. And it expects within that forward delay time for it to reach throughout the topology, right? Your spanning tree. All switches in the spanning tree. Sorry, that is the aging time. That is the aging time. So if I am downstream, switch A is a root, switch B is downstream. Switch A receives a TCN, and so switch A starts to transmit TCs, BPDUs with TC set. When that TC reaches switch B, it knows there's been a topology change, and it reduces the aging time from 300 seconds to the same as a forward delay, which is 15 seconds. And then it ages out the MAC address table. TCs will be sent for the forward delay plus the max age, which is 35 seconds total. Where I get this wrong a lot is I put 20 seconds here for the max age time on a topology change notification. I keep wanting to put 20 seconds instead of 15. That's why here, instead of putting 20, I used to have 15 here. Now I just put the forward delay. It's equal to the forward delay. So that's a reminder to me next time I see this that that's a forward delay, which is 15 seconds, right? RSTP is a lot different in this regard. It's much more efficient. So the hello timers are sent every 2 seconds, but they're not relayed. And what that means is when the root bridge sends the BPDU from A to B, for example, B is going to wait for that BPDU to arrive, and then is going to relay it on its designated ports. Right? It's just basically making a copy of that same frame. Spanning tree is not like that. So spanning tree, when switch B realizes, it knows what the BPDU is for the root. It's designated its root port. It's not going to wait for BPDUs to come in. It is also just every 2 seconds going to send a copy. It's more efficient, right? It's going to send the root BPDU, a copy of it, on its designated ports. Important distinction. And then the forward delay, it's not really, there isn't really per se the forward delay. Essentially, if there are 3 missed BPDUs on a port, on a root port, there are 3 missed, the port will transition, right? So that could be 6 seconds, essentially. There's no max age time really equivalent or aging time. It just works differently. And when a topology change occurs, it transitions immediately. And it flushes out the MAC table. And there is no TCN process. So the root bridge, switches don't wait to receive a notification and then an acknowledgement. When there's a TC, it goes up the tree, down the tree, and it transitions immediately. The root bridge it does use 2 times a TC while timer. I couldn't get really specific information on how that works, but it's essentially, it's going to send it for 2 seconds. And then the other switches, of course, are all going to propagate copies of that BPDU, the new BPDU, and make that transition as well. So much, much faster. Okay, that covers that topic. What else we got here? Okay, this was interesting. There's a link down here, folks, that I kept hitting on. And that is PVST, PVST Plus, and interoperability with 802.1D and 802.1Q. This is complicated. I try not to get too much into the weeds here, but it was helpful because I've always wondered, when you look at Ethernet MAC addresses, and I've got a table here, and this is important to know. So when you got BPDUs, why is it that some of them go to this oddly varying, let me just check an email real quick and make sure that we are, yeah, we're good. So you've got native, and this is actually wrong. I need to correct that. I'm going to double check that, but you got non-native VLAN BPDU is using 0180, and then you've got this native VLAN spanning tree BPDU. This is particular Cisco devices, and they're using the 01000CCC.CCCD, which is very similar to CDP, DTP, PAGP type of packet. Why is there such a disparity here? How am I going to remember which is which, native and non-native? Well, I found out today really what that has to do with, and that has to do with the fact that Cisco early on had PVST for private VLAN, or not private, but for per VLAN spanning tree, and it used, of course, ISL initially, and it was using these types of format of packet. Well, then at a certain point, IEEE had spanning tree protocol, and of course DOT1Q. So now Cisco has to have a way to sort of marry the ISL and the DOT1Q capabilities into their implementation of spanning tree. So that's when they came out with PVST Plus, and it is interoperable with both ISL and DOT1Q. But it uses a different type of BPDU than IEEE, the standard BPDU. And I've heard other vendors complain about this. I remember a project where I had I think it was IBM switches and Cisco switches, and we were having issues with tagging and the native VLAN and the default VLAN, and that's when I first learned about this difference. I've never seen anything explaining it though. Never really looked, but this article does a great job of explaining it. It's a Cisco doc. And they even have a chart here showing you the packet formats. Or I thought they did. That must be a different doc. But yeah, when you look side by side the BPDUs on that Cisco uses and the standard IEEE 802.1d, the address is different. Well, actually what Cisco will do for interoperability, it will send both what's called an SSTP, which is shared, SSTP BPDU. I looked this up. I knew it earlier. It might be on here. Yeah, shared spanning tree. Not the same article. Basically, IEEE BPDUs are sent to the IEEE MAC address, this one. While mentors share a few resources well, and a few topics, just stay in LAN and Discord network link bucket. All right, man. Thank you. Appreciate that. Awesome. Yeah, SSTP stands for Shared Spanning Tree Protocol. Cisco's older PVST used ISL, while IEEE used 802.1Q. Hence, Cisco came up with PVST Plus as a way to interoperate between these two protocols. So yeah, you're actually looking at two different kinds of BPDUs. And you can look at the packet captures, and you can tell by the IP or the MAC address, the multicast Ethernet address that's being used. And Cisco PVST Plus, if you're running PVST Plus, which any switch since who knows when is going to be running that, you can you're supposed to be interoperable between both kinds of BPDUs. You can send both if needed. So I thought that was pretty cool. And then we'll get into this longer section, which is about, oh, there's a good RSTP explainer document here as well, which I've linked. I'm just going to throw all these in here too, guys, gals, if you're following along. Policers. So for policers, it wouldn't fit in the agenda. It was just too much. Like, okay, I got to make what's essentially my own sort of blog, I guess. But what I could not explain coherently yesterday, I should be able to explain today, and that's my goal. So remember, there are three types of policing generally: single rate 2-color, single rate 3-color, and dual rate 3-color. And what I went into today is trying to understand this formula of how it's calculated. So we're going to walk through that. We're going to start with single rate 2-color. 2-color being green and red. So green in this case will be conforming, and red will be exceeding your rate. And the formula for this averaging interval is TC equals BC divided by CIR. And what that means is TC is time intervals. So you're splitting up 1 second into a certain number of intervals that you want to use to measure how you're sending traffic. And that's going to be an average, right? You want to come up with some sort of average. And you could come up with as little as, for example, 8. So you could cut a second up into 8 pieces. And you could say, which is kind of long when you think about milliseconds, right? So a millisecond is 1/1000th of a second, and voice. Basically, when you cut up time intervals by 8, that's 125 milliseconds. That's a long wait for voice. So you can get really granular here, and basically what you're going to do is you're going to create these buckets for measuring and trying to keep a steady rate of interface transmission, based on how big or how small you want these intervals to be, right? So we're going to do 8 just for grins here. And then you have your BC, which is your burst commit. So in other words, really what I want is to know an interval. I want to split up things by an interval. And then as a byproduct of that, I need to know how much data do I need to sort of track, or what sort of bucket do I need to build, what size for that interval, right? And of course, all this is based on the committed information rate in bits per second, the CIR. So, and I'm going to walk through these individual components, right? But let's say, for example, you have 100 megabits per second interface, fast Ethernet. But your service provider, or just you as an admin, you decided, all right, I've got 100 megabit interfaces, and I've only got 5 gigabit uplinks. So I'm over provisioned on this switch or on this router, whatever the case may be. So I want to do a committed information rate of 50 megabits per second. By the way, remember, guys and gals, when you transmit on an interface, you can't really slow down the transmission of an interface. So if you send that interface for half a second, you send it 100 megabits per second, it's going to transfer at 100 megabits per second as fast as it can. If in the next half second you send it a burst of 50 megabits per second, well, as quickly as it can queue, it's not going to transfer at 50 megabits per second. That interface on the wire is always going to transmit at the same speed. That's why we have policing to sort of control against an average that we're coming up with. We want to control that, in the case of policing, over subscribing that interface and randomly dropping packets, right? Or tail dropping packets that we don't necessarily want. So let's say we set it at 50 megabits per second. That's what I want to send on this interface. I really don't want to get that much above 50, right? And you decide, all right, we're going to do our pacing or our intervals. We're going to do 8 per second. Like I said, this would be very slow for a router, and there are limitations on certain platforms, how low or how high you can go on your interval calculations. But if you were doing that, you would set each time interval would be 1 second divided by 8, which would be 0.125 or 125 milliseconds. All right, the problem is you can't, on a device, you can't go to the CLI and say, this is my interval in milliseconds. You have to go about it in a roundabout way. So really, you have to sort of flip this formula around, and you can set the BC and CIR, the commit, the burst commit, and the committed information rate. And then the router or switch, the router's going to know, it's going to be able to derive from that formula what the interval is. Well, we start with our interval, and we flip this formula around. So we say the BC, so TC equals BC divided by CIR. Really, if I divide TC by CIR, I have this wrong, don't I? So it should be, no, I don't, I'm good. Yeah, it's multiplied. So if I multiply CIR on both sides of the formula, I would have the BC, which is my burst size. And again, the burst size we want to calculate in not bits per second. Even though we're doing a time formula here, we need to know in that interval of time, 125 milliseconds, what is the size of packet that I need to be looking for in bytes, right? So what we do in our formula is, let's say, we know what our committed information rate is. The CIR we said is 50 megabits per second. So that's 50 megabits every 1 second. So how many bytes is that in 1/8 of a second? How many bytes of that is in 0.125 or 125 milliseconds? That's what we need to figure out. So burst commit is going to be, we put 50 megabits times 0.125, which is our interval. Now we need it. This needs to be in bytes, right? Because we're gonna look at the size of the packet coming in and compare it against what we're allowed in that interval. So we take 50,000 or 50 million bits divided by 8, and we get 6,250,000 bytes times 0.125. So our BC, our burst commit, is 781,250 bytes. So in other words, let's say we were able to process consistently every 125 milliseconds, and we processed only 781,250 bytes, we would average 50 megabits per second. That's the idea. So what we can do is every 125 milliseconds, we look at the queue, the packets coming in, and see how big are they, right? And we can create a system for managing that. And oftentimes, most often, there's a token bucket analogy used. And essentially, it's 1 token per byte. So just imagine, every 125 millisecond, we're going to take a bucket, and we're going to drop tokens in there. In this case, we figured out, based on the rate we want, and based on the time interval we set up, it's 781,250 tokens in this bucket. And we're going to fill that bucket up at the start at 0. Let's walk through this, right? So 0 milliseconds on the clock. The bucket is filled with those tokens. Let's say 100 milliseconds has passed, and we get our first packet. And granted, this is not reasonable, right? 500,000 byte packet, we know. But just for illustration, right? It comes in, and we're going to see, okay, I've got this many tokens. this packet conforms with my burst commit. So I'm going to mark it green, conforms, and I'm going to go ahead and I've decided when something conforms, I'm going to forward the packet, and I'm going to take those 500,000 tokens out of the bucket. What am I left with? So I'm left with 281,250 tokens. That's great. Now at 125 milliseconds, I get 781,250 more tokens, right? Because that's our rate. What happens? Well, the bucket is refilled with 500,000 tokens to get us back to our burst commit. That leaves about 281,250 tokens that are unused, and they just get discarded in this two-color, single rate, two-color configuration, right? Now, let's say something else happened. Let's say at 110 milliseconds, I got another packet that was 500 bytes in size. Well, that does not conform. So that goes to our second color. In this case, it's going to be red. It exceeds our burst commit. In a lot of cases, what you're going to do, it depends, but a lot of cases, when it's red, you're going to just discard the packet. When you do that, you don't take away the tokens. 115 millisecond, another packet may come in that is 50,000 tokens, and it conforms. Forward it, reduced by 50,000. So hopefully you're seeing kind of how that works. What about three color? In three color, we add a new bucket called BE, or burst excess. And essentially what it does is it takes those tokens that are left over and spilled, and that's from BC, and those go into the BE token bucket. So you have two buckets. And now you sort of have those thresholds we talk about. You got, if it conforms to your burst commit bucket, you forward it. Let's say it doesn't conform, but you've got enough tokens left in the drain bucket, right? Or the BE, the excess bucket. So it exceeds, but in this case, exceeds is different because this is a three-color policer. So exceeds is no longer red in this case. Exceed is yellow. And in the case of exceed, you can make certain decisions. You can decide to forward it, or you could decide to forward it in a market, lower the priority, whatever you want to do, right? But let's say a packet comes in and there are not enough tokens in either the BC or the BE bucket. Well, this is in violation. That's the third color. In this case, it's red, and most likely going to drop it, right? So let's walk through these buckets. 0 millisecond interval. BC is filled with 781,250 tokens. BE has 0 tokens. At 50 milliseconds, we get a 500,000 byte packet. BC allocates 500,000 tokens. BE is a failover and capture bucket, and a three-color police are correct. So you're saying in this case, let's say you've got a two-color versus three-color policer. All right, so let's say with the two-color policer, you find that you're maintaining your 50 megabits per second rate. You're not bursting over that. But a lot of times, you've got a lot of tokens that are being wasted. So what's happening is this is a way to say, okay, most of the time I'm below 50, but it's not fair for a brief interval. If I go over 50, can I be allowed? Because you still got a 50 megabit per second there to work with, and it's never getting used. So with the BE bucket, you're able to say, all right, I'm going to let some capacity fill up there to use, and it's never going to go over really 100 megabits per second. We'll see why. But it's going to share out the load a little bit. Many of you have had circuits. I don't know if you ever purchased a circuit. Let's say you buy a 100 meg internet circuit, and the provider tells you it's burstable up to 150, which is great, right? Because maybe a lot of the times you'll be at 75 meg per second. But isn't it nice to have a little extra capacity? You can't do that, the provider can't do that for all the customers. Otherwise, it would just say you're at 100. But no, they're counting on the fact that you're not always going to go over 50, but when you do, not everyone is going to go over 50, and we can provide additional service and additional charge to the customer, right? Hope that helps a little bit. So yeah, BE is a burst bucket, burst excess. So at 0, it has 0. BC has its normal rate. We're trying to achieve 50 megabits per second. 50 milliseconds, 500,000 byte packet comes in. BC is like, okay, that conforms. I got this. You're green. I'm going to forward. Take out 500,000 tokens. Now I've got 281,000 left. BE still has 0 tokens. We hit that 125 millisecond interval. That's our TC, right? So then what happens is BC, it's like getting allowance again, right? BC gets his 781,250 tokens. But what happens to those leftover tokens? Well, to sort of even things out, this is where the 3-color policer, single rate 3-color policer comes in. It says, I'm going to take those 281,000 leftovers and I'm going to put it in BE, the burst bucket, the burst exceed bucket. So I'm going to have sort of, an optional rate here that we can use. Now, it depends on what you want to do. You could do with exceed, like I said, when it's yellow, you can decide to drop the packet, or you could decide to remark it. It depends on what your options are. Mentors definitely appreciate this breakdown. I'll definitely use my students. It's very helpful. So that's good, man. I'm glad. It can get confusing, man. It confused me. I spent several hours working on trying to understand this better. So here's what happened. Now BC has 781,000 tokens. BE has 281,000 tokens. Boom. 50 milliseconds passes. Gigabyte packet comes in. All right, just pretending here, right? So what happens here is, okay, we don't have enough tokens in the burst commit bucket. So it's not conforming. It won't be green. But we've got enough tokens in the burst commit and the burst exceed bucket to take care of this packet. And we've told the router that when it's exceeded, that we're going to forward the packet. So it gets marked yellow, essentially. And BC allocates all its tokens. And BE allocates the rest that is needed for this gigabyte packet. 280,750 tokens. It still has a few left over, 6,300 tokens. But that's all that's left until the next TC, which is going to be 250 milliseconds, right? So at 180 milliseconds, a 10,000 byte packet arrives, and guess what? We don't have 10,000 tokens in either of the buckets. So it gets marked violating. And in this case, we've told the router for violating packets to drop. Now, whenever we drop a packet, we don't remove tokens because we're not using any of them, right? We're just dropping the whole packet. So if another one came in at 190 and it had 6,000 tokens, we'd be able to mark it exceeding yellow and forward the packet. Okay, sounds great, right? Well, now we've got the last flavor, which is dual rate 3-color policer. I need some coffee. This is intense. All right. For dual rate, we have a difference with what we do with the exceed bucket. We still have 2 buckets, but B is not filled from spillover. right? Because as you notice in the first scenario, we essentially have, if it's based on the commit rate, then we will have 50 megabits per second burstable up to 100. We're not going to really go over 100 because we don't want to, because then we're going to have interface drops, right? But let's say we want to tweak that even more. Let's say we got 100 customers coming off this gear, and we're oversubscribed. We can guarantee, a committed information rate of 50 megabits per second for each customer, but we can't really afford for everybody to do 50 megabits per second burstable, or 100 megabits per second burstable. So what we do is we do dual rate. Instead of just letting tokens spill into the other bucket, we're going to have two rates. One to control our conform bucket, or BC burst commit, and another rate to control our, now you can use the same with dual rate 3-color policing, but just for purposes of this exercise, let's say you have a different rate and it's not 50, it is 75%. Now I know why I never want to work for. Yeah, service provider, man, is pretty interesting. Pretty fascinating stuff. And I'm glad I understand it better now. When I talk to service providers, I can. But really, shaping is really what in the enterprise what we do, right? Shaping is definitely an important thing. It can be a very good thing that we want to do on our provider-facing interfaces, on our CE routers, right? Probably don't want to do policing that much, but yeah, service provider definitely do it. Good point. And it can be fast. There's a lot of formulas, how people figure out their time slicing and all that. But yeah, for this dual rate, let's say we want the CIR and the PIR. PIR is peak information rate. So I'm going to say my CIR is 50 and my PIR is 75 megabits per second. And this is different because the two buckets are going to operate independently. There's no spillage. So every time cycle, like every 125 milliseconds, the CIR will get the equivalent, or the BC bucket will get the equivalent of the tokens it needs to maintain 50 megabits per second. The PIR, or the BE bucket, will get the tokens it needs to sustain 75 megabits per second. And it's the same calculation, really, for BE as BC. It's just we're using a different rate. So the PIR divided by 8 times TC divided by 1,000, right? Because we want milliseconds. So 75 million bits divided by 8 is 9,375 bytes times the same TC. We're using the same TC here. And you need to calculate these based on the same TC, the same time cycle. As far as I know, you can't really have two different rates based on two different intervals. I don't think you can. So anyway, as you can see here, we get more bytes per TC in the BE bucket. And what happens is, let's do a walkthrough. So at 0 milliseconds, the BC is filled with all the tokens that it gets, and the BE is simultaneously filled with, or allocate all the tokens that it gets at the start of an interval of 125 milliseconds. 50 milliseconds goes by, 500,000 byte packet comes in. Well, there's plenty of tokens in the BC bucket, right? That's what it's evaluated against, whether it's conforming or not. Again, we have our thresholds, remember? We've got conforming, exceeding, violating. This conforms. So it's going to be marked green. But what happens here is, although it's evaluated against the BC bucket, 500,000 tokens will be removed from both. Which makes sense, right? Because this is a higher information rate that you're trying to maintain. But they're removed from both. So we will have left over in BC in our commit bucket 281,251, in our peak rate bucket 671,875. 50 more milliseconds goes by. At 100 milliseconds, another packet arrived, 500,000 bytes. Okay, there are not enough tokens left to process that in our commit bucket, our BC. But there are enough in the exceed bucket. And again, this is not 281 plus this, right? This is either conform or exceed bucket. We're not going to take a little from both. But we see in the exceed bucket that we've got enough to handle this traffic. So BC will remain untouched. Still have 281,250 tokens. And BE is going to service that, and it's going to remove 500,000 tokens, leaving it with 171,875. But the packet will be considered yellow, exceeding. Now at 110 milliseconds, we still haven't gotten a refill of our tokens yet, right? Another 500,000 byte packet arrives. Now notice this. Between these two buckets, I think we've got enough, right? 2, 3, 450, no. Even if we did, this is going to be marked violating, and it's going to be dropped. All right, at the end of 125 milliseconds, both buckets are filled back up to their respective rates. And that's how the dual rate 3-color policer works. So, more granular control. And that is policing, folks. Whether you're doing 2-color, 3-color, single rate, dual rate. I hope that helps. Network lessons, man. I got to call, there's a couple of links in here that I posted earlier. If you want to go more in depth, these are definitely what helped me sort of start to get it. Great stuff. And now I just took, I was reviewing my failed boson questions, and I hit like 2 policing questions, aced them. I got that click moment, like that little ding, and I was good to go. So any of those I hit on the exam, I feel confident now that I'll be able to interpret the result. All right, we're going to wrap it up here, folks. We got yesterday's puzzler, which is what is MOS? And if anybody has it, feel free to post something in the chat. But gotta love deep dive now and also work. Thank you, mentors. Appreciate it, man. Yes, this is going to be brief. What is MOS? So MOS is, there's a link down here that you can look up more about this. This, of course, military occupational service. It seems like it when you're studying for the exam, man. It seems like you're belong to the military, belong to the CCIE. But yeah, this is a link here. Impacts of network on VOIP and MOS. That's probably a bad description, but 2451, hoorah! Yeah, MOS is mean opinion score. And it is related to voice because it is a rating system, a formula, some math that was determined to try to correlate the experience of a voice call, what that looks like, like what a ideal voice call looks like on the network, and every sort of grade or degradation of service below that. So I think a 5 in MOS score, calculated MOS score, is a perfectly fine phone call. In fact, this has a really good chart. It says, I don't know if this is official or not, but it says, 5 is excellent, 4 perceptible, not annoying, 3 is fair, slightly annoying, 2 is poor, annoying, 1 is bad, very annoying. So I know the voice guys that are part of sort of our infrastructure team, a lot of their tools, jitter is delay, like the interval of delay, and that is related to the performance quality of voice as well. Like you don't want, we're talking about bursting, you don't want a big burst of voice and then a long delay until you get the next batch. That's jitter. But MOS takes into consideration, jitter certainly impacts MOS, but other factors like latency also impact MOS, round trip times, things like that. And MOS is considered a more accurate reflection of the quality of voice. So that's what MOS is. And I got another little trivia question. What is the difference between LLDP and LLDP-MED? No problem, mentors. LLDP-MED, what is that, and how does it differ from LLDP? If you know the answer, that's great. Try to think of it without looking it up. And tomorrow you'll find out if you're right or wrong at noon. That's my intent, is to stream at noon tomorrow. And that's going to wrap it up, folks. I've got a couple of links here. I think I went over all these. Yeah, but I think we're all set. Thanks so much for tuning in. Appreciate everyone in the chat. Sorry for the interruption earlier. Had some business to take care of. It happens. That's part of live streaming and being a network engineer, right? Somewhat unavoidable. But yeah, 2 days left. I'll keep you all apprised. I'm going to get back to it. Thanks so much for stopping in the stream, folks. Hope you have a good weekend. Continue jamming. Make your plans. How are you going to jam? What are you going to do next? You going to lab? Are you going to study? Is your next exam scheduled? What are you doing? Feel free to tell us about it in the Discord. Hang out with us. Ask technical questions. Get their certification, track therapy. Yeah, see you tomorrow stream. Enjoy the fam. Thank you, mentors, man. I appreciate it. Y'all have a great night. We shall see you back here tomorrow on Land Tamara Stream.